Great. So the last talk of the first session will be given by Cameron Langer from Penn State. He'll tell us about the prescriptive basis at 2 loops and 6 points. Please.
Okay, so thank you to the organizers, first of all, for the invitation to speak at a conference that I've had the privilege of attending now for a few years. So as Song mentioned, I'll be discussing a prescriptive basis of 2-loop integrands at 6 points. This is work done in collaboration with Jake Borgelli and Yatsi Zhang, which should appear hopefully in the next month or so. It's also based on earlier work done with Enrico Herman, Andrew McLeod, and Jaroslav Trinka, which was the content of these 3 papers, and which in fact Enrico spoke about at last year's Amplitudes, and Jake spoke about the year before. So the big motivation for this this talk is about constructing integrand bases, which is a problem that we found in the last few years to be a worthwhile endeavor, both from the perspective of matching amplitude integrands, as well as from the perspective of actually performing the loop integrals. So in the context of generalized and prescriptive unitarity, we've constructed, the central result of this talk will be a 3-gon or triangle power counting basis of 2-loop integrands at 6 points. So in the construction of a basis, you first need to discuss your choice of power counting, which is a slightly subtle problem in the non-planar sector. So in particular, once you specify your choice of power counting, you can talk about the size of your integrand basis. And then the much more difficult problem is about how to construct a good basis. And obviously I need to specify what it means to be a good basis. So what that word is doing a lot of work in this statement. And that'll be one of the goals of this talk, which will be to emphasize that our particular integrand basis, which is fully diagonalized in cuts or field theory residues, is very, very nice from the perspective of matching amplitude integrands, and hopefully from the perspective of actually doing some of these loop integrals. So once again, we will construct a fully diagonal basis of integrands, which has the property that when possible, these integrands are d-log. They have only logarithmic singularities. They're pure, so they're normalized to be 1 on all residues. And furthermore, they're stratified according to their infrared behavior. So the claim is that every integrand basis element, which is defined on a soft or collinear residue, will be infrared divergent, and the rest of the basis we expect to be infrared finite. And so the purpose of my talk will be to discuss how we constructed this basis and to argue why it's a good choice. So along the way, we'll find new representations for a new representation for the MHV 2-loop 6-point integrand, and as well as a representation of the NMHV integrand as well. So I don't have to talk much about the background of or the utility of generalized unitarity. It's one of the most successfully utilized tools in the Amplitudes community, which has a long history of with great success. But the basic idea is, of course, very simple, which is that amplitude integrands are rational functions, and as such, they can be expanded in a basis of rational functions in any cut constructible field theory. And the coefficients in this expansion are fixed by matching a spanning set of field theory cuts, which are computable from first principles in any quantum field theory as on-shelf functions. And so in particular, this unitarity method reduces the problem of constructing loop integrands to one of linear algebra. And of course, as soon as you're solving a linear system, your choice of basis integrals, these lowercase b's in this expansion, tends to have a very strong effect both on the simplicity of your result and for what properties you may or may not make manifest in this representation. So if we just considered a very simple a schematic one loop example, we can see that if we use a basis of scalar integrands, then constructing an amplitude with bubble power counting would amount to using scalar boxes, scalar triangles, and bubbles. And if we proceeded from the traditional unitarity approach, we would first match the coefficient of the scalar boxes using the quadrupole cuts. Schematically, it's just given by this on-shell function. Then we would proceed down to this scalar triangle, match it on some field theory cut associated with the triple cut, but we would then have to subtract off the pollution from the scalar box, and that pollution would then filter down as well to the scalar boxes. And so if we just kind of take this naive basis of integrands, or somewhat arbitrary choice of basis, then the coefficients will, of course, be an arbitrarily complicated linear combination of field theory residues. This is despite the fact that each cut in field theory is very simple. Right? It can be computed from as an on-shell function. So the basic idea behind the prescriptive refinement of unitarity is that we should reorganize our calculation. We should take a sort of bottom-up approach, and we should define the elements of our integrand basis to match a single cut in field theory. So each integrand is normalized on a single cut, and these basis elements are then defined to vanish on all other defining cuts. So in the perspective of this one loop example, we would first normalize the bubbles on some cut associated with the bubble cut. Then we would go up to the triangles and define them on a single field theory residue associated with the triple cut, and then also demand that they then vanish on the contour or residue we use to normalize the bubbles, and so on. So the boxes would be defined by being normalized to be units, let's say, on the quadrupole cut, and vanishing everywhere else that we use to construct the rest of the basis. Of course, we can't make our integrands vanish on every other cut, because there's just many more cuts in field theory than there are elements of our basis. But as long as we match a spanning set of cuts, then by completeness of the basis, every other cut will just be matched via residue theorems. So the recipe at higher loops, in particular in the context of this talk, will just be 2 loops. The workflow for constructing a good basis of integrands is to first write down an arbitrary basis, which means you need to know the size of your basis, which is dictated by your choice of power counting. Then step 2 is to enumerate a spanning set of cuts or contours or residues in field theory. And then step 3 is to diagonalize the basis that you started from with respect to the choice that you made in step 2. And depending on the choice of cuts that you make, you can make various properties of your answer manifest. And the nice thing about being at 6 particles, of course, is that there are no singularities worse than logarithmic singularities or double poles in certain cases. We never have to worry about elliptic cuts or anything worse than that. And so at 6 particles with 2 loops with triangle power counting, which I'll define in a moment, the basis can be stratified according to make polylogarithmicity manifest, purity manifest, and the infrared structure as well manifest. So I'll now, in the rest of the talk, I'll discuss these 3 steps, and as well as the properties of the integrand basis that results from this workflow. So step 1 was covered in a recent paper with Jake, Enrico, and Yara, where we discussed a non-planar or graph theoretic definition of power counting. So just to remind you, this size of the integrand basis that we start from depends on both the space-time dimension, which in this talk will only be d = 4, and your choice of power counting. And at 1 loop, the power counting is a very obvious thing. It just reflects the way that an integrand scales when you send a loop momentum to infinity. And because there's a canonical loop momentum routing for planar graphs, this is a meaningful statement. And so in this context, a 1 loop integrand scales like a triangle at infinity, whereas in triangle power counting, if it goes like 1/L² cubed, when L is sent to infinity. So in this paper, we introduced a graphical notation for loop momentum dependent numerator insertions. So we draw this red circle on top of the propagator to indicate a loop momentum insertion, where it's very convenient to use as your basic building blocks the span of generalized inverse propagators, which is what we mean by this square bracket L. So in 4 dimensions, this is a 6-dimensional space, which can be spanned by these 6 elements. So you take L squared, you take dot product of L with 4 independent vectors, and then the scalar. And as we'll see, this basis is also naturally decomposed into what we'll call top level and contact term degrees of freedom, but that will be more relevant here in a moment. So using this notation, we can describe the space of all one loop integrands with triangle power counting in an overcomplete way by saying it's arbitrary linear combinations of scalar triangles, boxes with a single loop momentum insertion, pentagons with 2 insertions, and so on and so forth. Of course, the nice thing about 4 dimensions is that pentagons and higher in this are entirely reducible in terms of scalar triangles and boxes with a single loop momentum dependent numerator insertion. And essentially this complete description of the basis is what was used by Jay, Chiara, and Simone to construct the so-called chiral box expansion at one loop, which is kind of the one loop version of the 2-loop basis that we constructed that we'll end up with in this result. So at 2 loops, why is power counting more subtle? And it's because there are non-planar graphs, of course, so there's no canonical way of routing the loop momentum. And so you cannot just, there's, if we take, for example, this graph, which we would call, in the context of our building bases of loop integrands paper, we would call it gamma 312, that if I ask how many L1 and L2 propagators are there in this graph, then if I draw the graph in the first way, you'd say it's 4 L1 propagators or L1 dependent propagators and 3 L2s, but nothing prevents me from drawing the graph either as the second or third graphs. And of course, the number of propagators then changes. And so it's not so simple to say what you mean by triangle power counting if you're referring to a particular choice of routing of the loop momentum. And so the idea behind our recent paper was to define the power counting of a graph relative to its contact terms or relative to its daughter graphs, which are generated by edge collapses. So to explain what I mean by that, so we define the scaling of a graph or an integrand at multiple loops as in reference to what we call scalar pgons for pgon power counting. So we define a scalar pgon as an integrand whose graph has girth p, such that every daughter of the graph, which is the graphs obtained by single edge contractions, has girth which is strictly less than p. So for 3-gon power counting or triangle power counting, which is once again the subject of this talk, the set of scalar 3-gons is very easy to list. For any choice of p, this is a completely straightforward task. But there are just these 2 graphs for triangle power counting, which we would call gamma 303 and gamma 212. So the kissing triangle topology, and then this double triangle, which is the second. So every graph which scales at infinity, like either of these 2 scalar 3-gons, we say has lives in the triangle power counting basis at 2 loops. So just as for some examples of such integrands would be this first topology, which is gamma 222 with a single loop momentum dependent numerator insertion in the middle loop. You can see that if you contract exactly that edge, you land on the gamma 212 topology. And so that's why this integrand would be considered to have triangle power counting. So this rule also gives us a definite prescription for actually constructing the right numerator space. So as an example, let's take this 7-propagator graph, which we call gamma 322. Then to write down the space of allowed numerators for this graph topology for triangle power counting amounts to constructing all edge collapses of this graph, which land on either of the two scalar triangle topologies. And for this example, there are 3 ways of collapsing edges to get to either of these two graphs. In particular, we could collapse 2 of the red edges, and that takes us, that takes us to one of these two graphs. And the rule is that for each edge you collapse, you write down one factor, one corresponding factor of the loop momentum vector space. So for the first path, you just write down L1 squared. For the second path, which collapses a red and a blue edge, you write down L1 times L2. And the third is collapsing 1 red and 1 green edge, and that gives you L1 times L1 minus L2. And the full numerator space is just the direct sum of these 3. And in 4 dimensions, it's very easy to just, and in any number of dimensions, it's easy to just count how large is this vector space. And in 4 dimensions, it turns out to be a 55-dimensional space of numerators. In this case, it's very easy, or it's very worthwhile to decompose this 55-dimensional space into a 10-dimensional space of numerators which cannot be spanned by contact terms of this graph, which meaning it can't be spanned as in terms of inverse propagators of this graph, and then a 45-dimensional space which is spanned by contact terms. So we can do this, we can repeat this for every such 2-loop graph, which has these 2 scalar 3-gons as daughters. And so the result at 2 loops was given in several of our older papers where, so this is the complete list of irreducible integrand topologies at 2 loops. So this is everything we need to consider. And we've also then listed the total rank of the numerator space, as well as how it separates into top level and contact terms. So the red numbers are, is the rank of the numerator space modulo contact term degrees of freedom. So this is the size of the basis that we're starting from. So how then do we construct nice numerators, or how do we write down a spanning set of contours? Well, for 8-propagator graphs, this is quite simple. So we take, for example, this Penn box topology, and according to our definition of power counting, this has 120 degrees of freedom in the numerator space, and 4 top-level degrees of freedom, which cannot be spanned by contact terms. Conveniently, for every 8-propagator integral or integrand, the number of top-level degrees of freedom is the same as the number of solutions to the cut equations. And so the natural place in loop momentum space to normalize the top-level degrees of freedom of this graph are exactly the points in loop momentum space which cut all 8 propagators of this graph. And we can represent these cuts or contours graphically using these on-shell functions. So these are the 4 colorings of this scalar graph, which correspond to solutions of the cut equations. These are our the 4 spanning set of contours for this graph at the top level. And it's then easy to construct numerators which are block diagonal on these 4 contours, and they're conveniently described in terms of these brackets, which, if you're unfamiliar, are nothing but chiral traces. So depending on the order of the bracket, it's either a trace plus or a trace minus. So there's nothing mysterious there. But these brackets turn out to be quite useful from the perspective of constructing nice numerators. And so that's what happens at 8 propagators. Of course, if we now go to a 7-propagator example, it's a little less obvious what the spanning set of contours should be, because of course there's only 7 propagators. So necessarily the codimension 8 contours or residues must involve composite leading singularities. And in particular, our choice is to use as many physical leading singularities, meaning singularities associated with infrared divergences as possible, and match as many of these manifestly as we can. And once we run out of these places in loop momentum space, we fill up the rest of the basis with contours defined at infinity. So to illustrate how that works, we can consider this gamma 322 example where there are 10 top-level degrees of freedom. So we need 10 contours on which to normalize these these integrands. And again, it's relatively straightforward to just enumerate a nice set of 10 contours. And so to illustrate the meaning of these pictures, so in these pictures, a dashed line represents setting the momentum flow through that edge to 0. So that corresponds to soft singularity, and an encircled vertex means that we set the momenta at that vertex to be collinear. And finally, a loop, or a sort of extra loop drawn in the diagram in red here, indicates that on this 7 cut, we send the loop momentum running through this cycle to infinity. And that defines the contour on which we normalize the corresponding integrand element. And so in particular, for these contours normalized at infinity, note that for an amplitude which does not have poles at infinity, such as maximally supersymmetric Yang-Mills, it's necessarily every integrand which is normalized at infinity will have a vanishing coefficient, since the amplitude vanishes there. And so once again, once you've specified this choice of 10 contours, it's a relatively easy problem to construct a block diagonal basis of 10 numerators. Here you can see that in order to make the system diagonal, we had to add some of these integrands. In fact, almost all of them have support naively on these 2 contours defined at infinity, and so some of them require some slightly more non-trivial numerators. But again, this is a relatively straightforward problem, and we can repeat this for every topology which appears at 2 loops and 6 points. And that's our starting point, which is a block diagonal linear system. There's only one subtlety, which is that for occasionally there are integrand topologies where there are inescapably double poles floating around. So if we look at, for example, this 2-2-2 topology, there are 6 degrees of freedom, but there turn out not to be 6 independent contours which are logarithmic. So since the scalar degree of freedom is an allowed numerator, it's relatively easy to see that if we set the momentum flowing through A and C to be collinear to P1 and P2, then on this residue, the scalar numerator, or the scalar integrand here, inescapably has a double pole on any further residue. And so this is sort of unavoidable part of the basis. But note that the effect of diagonalizing the basis is that every basis element which is not normalized on such a double pole will necessarily be free of all such double poles. So they end up—
you have 3 minutes before the questions.
Okay, yeah, thank you. So necessarily they will be free of these double poles. And so this is an unavoidable part of the basis, but it ends up not appearing in the final representation of any amplitude which is free of double poles. So finally, the last step of the basis construction is global diagonalization. And because we construct a block diagonal basis for each topology, diagonalizing the full field theory cut matrix amounts to iterative subtraction. So returning to this gamma 322 example, we define the 10 top level degrees of freedom of this topology, but there are 45 contact terms, and the contact terms are then used. They are fixed by the statement that our system should be diagonal in cuts. So what that means is that for this parent topology, you consider all daughters, meaning all graphs generated by edge collapses of this graph, which include, for example, these two examples here. And for every contour associated with a daughter graph, the parent must vanish on all such contours. And so this is the statement which finishes the global diagonalization, which ends up being something like a 3,200 dimensional linear system. And our final result is, again, I'll just emphasize a basis which is almost entirely D-log, which is pure and cleanly separated into IR finite and divergent integrands. And then representing an amplitude in this basis is totally trivial. So for MHV, you just then list the MHV leading singularities in the choice of the spanning set of cuts. you do the same thing for NMHV and you obtain the amplitude integrand for that helicity configuration. So in this basis, you just, once you construct the basis, it's essentially trivial to match the amplitudes. And finally, just I'll wrap up here in the next 30 seconds. Our basis is, with some outlook, our basis should be expected, we expect our basis to be quite useful for direct integration. We'd like to generalize it to all multiplicity, which will require solving some subtle issues involving these nastier singularities, which can appear beyond 6 points. We'd like to upgrade our basis with mu terms needed for dimensional regularization. And finally, we expect that because our basis is partitioned into IR finite and divergent integrands, that we might be able to discuss a term-wise or locally finite representation of the two-loop ratio function, which would be an interesting follow-up to this basis construction. But I think that's all I wanted to say, so I'll just say thank you for your time, and that's it.
All right, thank you. Time for questions. Now, Oliver?
Yeah, thanks a lot for a pleasant talk, Cameron. Now that you succeeded to get a loop integrand for 2 loop 6 points, what are the perspectives to rewrite it a bit such that the UV power counting becomes improved? I mean, no triangle property, no loop momentum on boxes, linear for pentagon, quadratic for hexagon. How easy or hard would it be for you to produce such a representation?
Yeah, so I think it would be quite difficult. I mean, well, it involves, of course, as you obviously know, the UV behavior of Yang-Mills is better than triangle power counting. So, why in the world are we using triangle power counting in the first place? And the reason is that in order to, if you want to solve this the analogous problem for box power counting, you need integrands with more than 8 propagators. And so if you were to take our representation and you tried to write it to make this improved UV behavior manifest, you would end up with integrands with more than 8 propagators. But I'm in the details, I'm not exactly sure how difficult that would be. Okay. It's much more sort of arbitrary to construct a prescriptive basis of integrands which involve more than 8 propagators at 2 loops, because it's an overcomplete basis. And so you have to make some arbitrary choices there.
Oh yeah, thanks. And yeah, indeed, I understand that you have good reasons to start as you started. So I was wondering whether there's an educated way of adding zeros to your existing result. Yeah. Okay. Thanks a lot.
If I could chime in there on that, the analog at 1 loop, you can confine all of the parity odd integrals to being triangle power counting if you'd like at 1 loop. And so you can recover the scalar box expansion as just the parity even part of something with triangle power counting. And maybe that's possible here. So you could arrange all of the non-vanishing integrals to be boxes, and then the ones that are vanishing to be triangles. But yeah, purely box power counting would be difficult, as Cameron said.
Okay. Thanks.
More questions? Comments? So Cameron, you mentioned a goal would be to achieve some term-wise finite representation for ratio function. Is that can that be achieved first for the planar case, or even there it's not clear if your result will give that term-wise finite representation?
Well, yeah, no, in the planar sector, yes, it would. I mean,
okay,
yeah,
okay.
That you can
for all multiplicity.
Well, no, we don't have
for 6 point.
Yeah, just for 6 point. I mean, we have not yet constructed the all multiplicity generalization of this basis.
Okay,
but,
okay.
Yeah, of course, get a termwise finite representation of the two-loop ratio function. In the planar case, you don't need this basis. You can just you can just use this the two-loop basis that Jake and Yara constructed a while ago. You can manifestly show that these infrared divergences cancel.
That is already termwise.
No, it's not. It's not manifestly termwise.
Okay.
Finite. It does take some work, but yeah.
Okay. Thank you. Are there any other questions? If not, let's thank Cameron again. And we thank all the speakers of the first session. We'll take a 30-minute break, and I guess we can keep discussing during this break.